Thank you very much, Mark, for the kind introduction, and thank you for inviting me. Today I want to talk about a family of systems which in academia are often referred to as spoken dialogue systems. Now in industry you often call them chatbots, virtual personal assistants, or voice-based interfaces. So the common feature of all these systems is that you talk to them and you hope that they will talk back to you and somehow make sense when they talk back to you, right? And the methods I want to talk about or focus on today are data-driven machine learning-based methods. And I want to give you a brief overview of what's currently done in the field and give you my impression, what I think works and what doesn't work, and the future challenges in this field. So I'm part of a bigger group at Heriot-Watt University. Heriot-Watt University is the Technical University of Edinburgh, and we are a group called the Interaction Lab, which consists of 5 faculty members, about 10 postdocs, and an equal number of PhD students. And we are working on, in general, interactive systems, including human-robot interaction, natural language processing, and machine learning. I'm heading the natural language processing group, but before I start my talk, I want to acknowledge all the brilliant people I work with in my group. I'm also heading a couple of research projects which are mainly funded by the UK Research Council, but we also have a couple of collaboration with industry. So I'm working on natural language generation, transfer learning for dialogue systems, automatic quality estimation, personalized human-robot interaction, the Amazon Alexa challenge. So that's something I'll come back to later on and tell you a little bit more about my experience there. And finally, sentiment analysis for Arabic, and we won the semi-eval task on this last year. So what I really want to talk about in this talk are talking machines. So Siri is one of the best known examples of a virtual personal assistant. However, I think since Amazon Alexa or Amazon Echo came along, so that's this device here, people really start to see the value in voice-based interaction. So this week, Google has released a similar tool shown down here, and I think, at least for myself, it's very much true that I prefer talking to Alexa in my home than I do to Siri on the street. And I very much in my personal life, actually the voice-based interaction I have since I have an Amazon Echo very much increased. This isn't supposed to be an advert for Amazon Echo, by the way. It's just to show you that it really depends on the context you're using these devices in. And also that with the introduction of a proper hardware device, now I think it's the right time to actually focus on developing these type of systems further. So Microsoft agrees with me. So Microsoft's CEO, Nadella, says, bots are the new apps because they fundamentally revolutionize how computing is experienced by everybody. So what that means is that voice-based interaction in a way solves the too many apps problem. So instead of getting out your mobile phone, finding the right app, opening the app, trying to learn the interface, clicking through all the information, what you do is you just talk to your device using your natural means, how you would talk to another human being, and then hopefully, fingers crossed, the device will give you the right answer, right? And that's what we're working on. When you look at market prediction, they also are very positive about this area. It actually comes third, right after autonomous robotics, and to my surprise, even before neural networks. So by now I hopefully convinced you that this is a good area to be in at the moment. But what about the research? And I especially want to focus on, as I said before, on data-driven techniques for building these systems, because that's my main research area I'm interested in. And I'm going to start with what I call task-driven systems. So these systems you use for solving a concrete task. So for example, you want to book a restaurant, you want to find a flight, you want to call a contact, on your phone. So you've got a very clear goal in mind, and it's crucial that the system understands what you're looking for, right? And there is a standard architecture which people use for building these systems, and it's a modular architecture in sort of a pipeline approach where you go over here for a change, where you start with the speech recognizer. So the speech recognizer takes the user utterance, the waveforms, and translates it into words. And then you've got the spoken language understanding module, which parses it in some sort of semantic representation. So commonly what we use in my research area is what we call dialogue acts. So this is a very underspecified semantic representation which captures a vague notion of what the user tries to do. So in this case the user says, I'm looking for a cheap restaurant, and we represent it as in form, price equals cheap, and possibly type equals restaurant, right? So this abstract dialogue act is then used to build up a context, and the context is used by the dialogue manager to reason of what to do next. So the dialogue manager is somehow the brain of the system, and it also can query external sources such as a database. And then it's supposed to come up with a strategy, so a strategy of what to do next, how to reply to the user. And again, the strategy is formulated at this abstract level of dialogue acts. So you have something like present all the restaurants where the price equals cheap, right? And then this dialogue act gets fed into the natural language generation module, which then translates this abstract act into concrete natural human language, meaning words, and then you synthesize that back using the text-to-speech module, and that's what the user then eventually hears. So in my previous research, I've mainly worked on dialogue management. I'm currently very much interested in natural language generation and the combination between those two, and I've also worked a little bit on text-to-speech. So as I said, task-based systems are very much focused on a concrete task, and we usually use a representation of slot value pairs to represent this task. So this is some sort of unspecified semantic frame where you try to fill slots, and you determine, okay, which slots did the user already provide. Ideally, you'll add some sort of confidence value, how confident you are that you got the speech recognition right, and then you prompt the user for the missing slots, right? So that's how we represent the task. And then on top of that, what's often done is to formulate if-then rules of what to do next. So that's a very common approach in industry and also in academia, and it's often formulated as a finite state automaton, maybe implemented in voice XML or similar formalism. Now there are popular platforms like API.ai, and so in the end, it's really up to you, to the system designer, to come up with these if-then rules to implement what you think this problem or this task constitutes. So when you think about the definition of what you're trying to do in dialogue systems, and this is where I like to quote myself, so we defined a dialogue system as a computer agent that interacts with humans by understanding and producing spoken language in a coherent way. And that last bit, in a coherent way, it's where it becomes difficult to capture that with rules. The reason is that you actually need to do quite a lot of planning. So you need to build up a history of what happened and then plan ahead of what to do next. You need to adapt. You need to adapt to the user, but you also need to adapt to the current context the dialogue happens in. And finally, you need to be robust, right? You need to be robust against speech recognition errors, but you also need to be robust against unforeseen situations. And unfortunately, when you interact with real people, they do a lot of unexpected things. So everybody who deals with real people in the research will have had this problem that you think, oh, I designed this really good system, thought about every possible interaction I could possibly have with this user, wrote all these rules, the first user comes along and it completely breaks the system, right? So robustness is key to these systems. And that's why data-driven machine learning methods are promising in this area. So when we think about task-based, when we stay with task-based systems, there are two main research areas. One is belief monitoring using what we call partially observable Markov decision processes, or called POMDPs, and the other one is action selection or policy optimization using reinforcement learning. And reinforcement learning is often used in robotics. So the idea is that you've got your little agent here, and the agent takes actions, and the actions can change a stochastic environment. And then the agent observes what new state the environment is in, and it also gets a reward, how good or how bad this new state is following the action it just took. And based on this experience, it updates a value function. In this case, it's the Q function, which defines the policy pi, and that's defined over states and actions. And that's computes a value looking into all the possible future rewards, given a discount factor, how far you actually look into the future, plus a state transition function. And this transition function is what we learn from data. So to give you an example how this actually works, so let's assume we're in a state, t-1, and we've got two possible actions we can take. We can ask the user, how many do you want, or do you want 3? So in the first case, given to our transition function, which we've learned, we have a 50% chance to end up in a good state, where the user says 3, and a chance to end up in a bad state, where the user mumbles something and we can't understand what's going on. For the second action, we know that we've got a high chance to end up in a pretty good state, but we also have some chance to end up in a very bad state. So by doing this over and over again, and accumulating this type of information from experience, we can then solve this, what we call Markov decision process, and find the optimal policy. So we know in each state S, which action is the best one to take to reach our goal. Right? And often the goal is then formulated as, for example, task success. Will I be successful in this task? Right. So in the previous example, I said I'll have a state, and I also assume that the state is fully observable, meaning that I just put features in the state, and it's often these slot value pairs I was talking about before, like price equals cheap, things like that. That's what we put in the state. And for Markov decision processes, we think we can directly observe all these states. However, when we think about spoken interactions, we have a lot of uncertainty from speech recognition. Did the user really say cheap? Or maybe he said moderate. We can't be sure because ASR, automatic speech recognition, introduces a lot of errors. And that's what is accounted for in what we call POMDPs. So in POMDPs, you start with a belief state where you have a uniform distribution over all the possible values. So in this case, we've got a uniform distribution of whether we think the user wants 1, 2, or 3 apples or whatever. And then we ask him a question, the user, how many do you want? And we observe the user reply, in this case 3 please, and based on this observation we update this belief state, so we shift more of our belief to the number 3. However, we still keep some of the belief distributed on the other values, meaning we are not entirely sure, maybe we misheard something. So this, at a later point in the dialogue, allows us to do belief revision. So if we have accumulating evidence that we actually misheard 2 for 3, we later on can easily change this belief. So that's what's called belief tracking in this area. And it makes dialogue systems much more robust. Right, so what are the challenges? First of all, it's data, right? So in order to train these systems, you need a lot of annotated data. So there's a lot of data out there of spoken interaction, but what we need is the annotation of dialogue acts. We need to know how far we progressed towards our goal. We need to know which state we're in. And in order to solve this problem, we've previously looked into training and simulation. So instead of interacting with a real user, we interact with a simulated user and train a system which learns in simulation. People looked into faster converging algorithms, domain transfer learning, and so on. Another more fundamental issue with these task-based systems is the interface with natural language generation. So I told you before that all these modules are sort of separately feeding into each other in a pipeline approach. So especially when you look at the interface between dialogue management and natural language generation, a lot of things can go wrong. So dialogue management determines what to say, so it spits out the dialogue act, and then energy determines how to say it, so it translates that dialogue act into natural language. And this translation can happen in many different ways, and often the dialogue manager thinks it said something, but the energy module actually said something slightly different. So this mismatch can be remedied using, for example, hierarchical learning, reinforcement learning, or more recently they looked into end-to-end neural architectures. And that brings me to the second part of my talk, where I actually specifically want to focus on these end-to-end architectures. So these end-to-end architectures are frequently used for social chatbots. So social chatbots are, in contrast to task-based systems, not necessarily trying to solve a task, but they're mainly there to entertain you. So we recently became interested in this task by joining the Alexa Prize Challenge. So I've entered our team into that challenge, and we were selected to be one of the 12 teams which competes for the prize this year. And if you win this, you actually get 2.5 million. Which sounds really good. However, when you look into what you're supposed to achieve, it's a very, very hard task. So the task is to converse coherently and engagingly with humans over popular topics and events for 20 minutes. So this contrasts with a Turing test, where you basically, the aim was to pretend or to mimic or to trick somebody into thinking that your bot was a human being. So this is much more specific. It means that you actually need to be coherent with respect to the history. So you have to keep track of what you said, you need to understand of what you said, you need to understand what the user said, and your next utterance must be making sense within that context. Being engaging, well, that's much more of a hard question. It's not an easy answer to when are you engaging. People might have different ideas what they find engaging. How will they show that they are engaged if they just type to your chatbot? Not so sure. Popular topics can mean anything, so we need to be prepared to actually talk about anything which comes to mind of the user. So it's a very hard task to solve. And when you look into what's out there, so current chatbots, what's out there, you might find very impressive examples. So this is an example I frequently play to my students, and they very much enjoy it. And some of you might know this video, but it's actually, it's very entertaining. So I'll just play it to you again for those who haven't seen it. Oh, it did work before. Where's the page? It was playing before. It did work before. The video, oh yeah, that's another problem, but the sound is the other problem.
That's good. I'm good.
Okay, very good. Okay, thanks a lot.
Hello there. Hi. How are you? Great. You? I'm okay. That's good. Are you good? Yes, I am good. I just said I was. No, you didn't. I said I was. So you are a robot? No, my name is Cliverbert. Yes, you are a robot and your name is Cliverbert. I am a robot. Yes, I know. Together we're robots. I'm not a robot. I'm a unicorn. But you said earlier that you were a robot. I did not. I thought you did. You were mistaken. Which is odd, since memory shouldn't be a problem for you. I've answered all your questions. No, you haven't. What is God to you? Not everything. Not everything could also be something. For example, not everything could be half of something, which is still something, and therefore not nothing. I would like to imagine it is. Do you believe in God? Yes, I do. So you're Christian? No, I am not. But you say you were not helpful, therefore you're a meaning. Are you saying erotic? That does not make sense. Don't you want to have a body? Sure. Or if what?
So after watching this, you might think, right, all our problems are solved and we can go home now. However, when you actually talk to Cleverbot, so it's a system online, you quickly learn that was a very lucky draw, right? And that's why that video became so popular. It's usually, the answers can make sense if you're lucky, but most of the time they don't make sense. So how did they actually build such a system? So this particular system is based... So talking again. Well, it's truly alive. Okay. Sorry about that. So this particular system is based on n-gram models. So it's just probability of one question, one answer following a question, and it's trained on big data. And the data is really the crucial element here. Because your answer is only as good as you can find in your data, obviously. So when you look at the architecture just described, it's basically a mapping. It's different from the conventional architecture. What it is, it replaces this whole bit, which is based on dialogue ads, with a direct input-output mapping. So you directly map what the user said to a system output. And they're also usually not text-based. So they're usually not speech-based. These systems are text-based. So a lot of uncertainty introduced by the speech recognizer actually falls away. So what they do, they learn from raw dialogue data, so they actually don't rely on dialogue acts, but directly encode a sequence of words. And that's a big advantage because no semantic or pragmatic annotation is required, and then you can easily harvest all this data which is available, such as open subtitles, for example. So there are different approaches to this input-output mapping. One is information retrieval, and that's commonly used by commercial systems. So they just index large corpora and treat it as an information retrieval problem. People are also looked into formulating it as a statistical machine translation problem. So you treat the user's question as the source language, and you treat the system's reply as the target language, and then you can apply statistical machine translation methods. And then, since 2005, the whole field basically shifted towards deep neural networks, and that's now what most people apply to this problem. So in this case, it's a very simple sequence-to-sequence model. So you encode what the user said and feed it into your decoder, and then you get what the system should answer. And then you train that on big corpora. So a very popular one is, I already mentioned that, the open subtitle corpus. Another corpus is from Twitter. Reddit is another corpus people start using, and then there is a corpus which was specifically collected. It's called the Ubuntu corpus, and that's people troubleshooting their Ubuntu system. So when you look into research papers, you think, oh, actually these systems are really good. You know, you look into the examples they put in their tables and you think, oh, that all makes sense. So in the first example here, the message is, well, I'm here to support you whenever you need me. The answer is, thank you, appreciate it, thank you. That sounds good. If a system would say that, I think we would all be satisfied. However, when you try it yourself, right, you get your RNN or whatever is your favorite model, you throw in open subtitles, and then you cross your fingers that you've got enough computing powers, and after some days, your system is ready and you try it out. You often find that the system is actually really boring to interact with, because most of the time it says, I don't know, or some other generic answer. So that's what you get if you train with these large corporates. The reason is that these deep learning mechanisms use maximum likelihood estimation. And one pretty good answer to pretty much anything you can say is, I don't know, or something generic like that. So people started to look into this problem, and there are various approaches trying to remedy this. And one interesting one is using deep reinforcement learning, where you combine reinforcement learning with deep architectures. So instead of putting slot value pairs into your state representation, you now train on deep neural nets. So you've got a vector space, word-based representation in your state space. Again, in order to do that, you need a lot of data, and what people currently do is to train in simulation. So they use an existing chatbot, such as Eliza, as a simulated user, and then they train the system with it. And when you look into the examples you find in the paper, at least, it looks pretty convincing. One big criticism I have, however, is when you look into the reward function, which tells the system what to do, right? What should it learn? The reward functions are terribly handcrafted. So the problem is we don't really have an objective measure. In our task-based systems, we used to be able to tell exactly when the system was successful or not, because it solved the task or it didn't solve the task. Here, they came up with something totally handcrafted. They even put the weights on just by the expert knowledge. So that's not good. And that brings me to the future challenges of this field. So, as I said, one is evaluation. How do you actually determine whether what you've learned or what you've built is actually good? So currently, what a lot of systems do, they measure goodness at turn. They measure goodness at turn level. So they look into two consecutive turns. Then, they use something like BLEU or Meteor. So those are measures used by machine translation to see whether what the system says is similar to anything they can find in the corpus. However, recent research has shown that these measures are not correlated to what humans think about the dialogue at all. So users rate the dialogue very differently to these automated measures. So they're not used to us. If our automated measure says, this is a great dialogue, and our user says, well, this is really disappointing, we can't use them for evaluation, right? So, so currently I'm looking into what's called reference-less quality estimation. So that actually gets rid of the problems we have had with BLEU and Meteor to try to always find an appropriate reference in the corpus. And then also we're looking into system-level estimates, learning from customer ratings. From the Amazon Alexa challenge, we actually get real customers interacting with our systems, which for an academic is very exciting, because usually we have to pay subjects, invite them into our lab, and they frankly don't really care about our systems. They just want to get paid. Similar to crowd workers, they don't really care about the interaction that much. You get very noisy feedback. Here we actually have real customers talking to our systems, and we can really see that in the scores and the feedback we get from these customers. So the other big problem we have with data-driven methods is that we need data, right? And even if we can use not annotated data, we still rely on what's in the data. So a couple of years, well actually last year, Microsoft released Tay, and probably most of you will have heard of the Tay incident. So Tay was a chatbot which learned from other tweets. And it very quickly started to be very inappropriate. So it learned to say all sorts of things which probably Microsoft wouldn't have endorsed. And in the end, it even told the user why it actually said all of what it said. And then Microsoft very quickly pulled the plug and yeah. So we have experienced something very similar with our Alexa system, actually. So we did the usual thing. We trained on open subtitles. We got all very excited because after a while of tweaking things, it started to make sense. And then Amazon said, well, okay, now we are ready to certify your bot to see whether we can release it to our customers. And they came back to us a bit worried and said, well, actually your bot is pretty inappropriate. It has very strong political views. It swears at the user, and it gives very inappropriate financial advice. So we said, sorry, there's not much we can do. That's what our system learned. Not up to us, and they weren't happy about that. So if you want to build a bot which is customer-facing, that's something different to actually building a bot which can learn from big data. So what you really need is a clean data set. So that's something we're currently working on. Right. So to conclude, to keep in time. So first gave you a brief introduction to what automatic machine learning methods are available for task-based systems. And the main problem is that for task-based systems, you rely on dialogue acts to measure the progress towards a goal. Then we turn towards chatbots, sorry, that's a typo, which are also called response generation systems. So they're end-to-end systems which rely on distributional semantics, and these bots aim for engaging strategies, whatever that means to be engaging. The challenges here is quality control and evaluation, getting clean data sets, and finally a big challenge is how to integrate these two systems, because what we really want in the end is a task-based systems which help us to solve a task, but also has social skills and is engaging and fun to interact with. And that's the end of my talk. Thank you very much for listening.
Okay, so thanks a lot, Verena. Great talk, I liked it. I think there's probably a couple of questions, and we'll take time for questions and postpone the break a little bit.
Yeah, so thank you very much for the talk. That was very interesting. What I've learned is that in the past, sometimes very simple methods have greatly improved specific approaches, like globally transition models we do search now, and then parsing of qualifications, for instance, able to achieve newspaper data. Do you think that for natural language generation there will be this aha effect at some point where, for instance, a new bucketing strategy or implementing deep search will greatly improve results, or do you think that it will be more along the lines of using more sophisticated methods, learning from rule-based approaches and trying to transition those into a statistical approach?
Okay, I personally think by tweaking deep learning algorithms even more, we won't get much further, to be honest. I think what you really need is some semantic understanding of what's going on in a dialogue, because currently with this end-to-end mapping, it's a black box. We don't know what's really happening. So to me, the exciting new research direction is really to combine models of semantics, of really understanding what's going on in dialogue with these deep learning approaches, and be able to control more of what was said before, and to understand what the system's actually going to say next.
I would even possibly go a bit further and say that
Yeah, I think that's very similar to what I said about trying to understand, you know, trying to get the semantics back into the dialogue, basically. So before we used very simple semantics such as dialogue acts, and we had to annotate them all. But there's also a very rich source of, you know, open semantic parsers, which we currently really don't use in dialogue systems. And then when you say, okay, it's not only understanding about, you know, the spoken interaction, but also what's understanding around you, what's to interact with the world. You know, there are interesting approaches to combine, you know, grounding language and vision, for example, to get an understanding of, if I say an apple, what is that actually outside of, you know, outside of my semantic mechanism? Is there something visual I can refer to? So there's interesting work of on combining or learning semantic representation through dialogue, for example.
All of this data which you're using seems to be very English-driven. Yeah. So, I mean, there is also the other world where also other languages being spoken, especially there's also a different mindset. And when we talk only, or when the research is mainly based on the English language, we have already kind of a bias if you looked at all of the other words. So, what efforts are done there to include also other languages, or is this only an English story going on currently?
So for the task-based systems, there's definitely work in other languages. So I personally, for example, know that there's a German system I've been working on. We had project partners working on a Spanish system. So there, it's mainly about, you know, training a semantic understanding tool for that language, gathering corpora, annotating them. For the end-to-end systems, the chatbot systems, I'm not aware of any system which is applied to any other language than English, mainly because they need so much data, right? And they use open subtitles. Now, open subtitles is also used by machine translation because they have all the subscript in other languages. So I expect that hopefully in the future people will look into other languages as well. But to capture the subtleties of a language, I'm not sure whether we get that from learning from big data. Because as you said, it's very much in the culture of how you interact, how you know, formulate something. So some of it we'll probably be able to learn from movies, for example, right? But not all of it. Yeah.
But as far as I understand, the problem you're trying to solve is a customer service problem, yeah? So you have to get customer service data. So you have to go with a company that has an operating customer service, one of those terrible things where you phone in, they say press 3, press 4, and all this. And that way you can categorize into various topics. And then you have to basically do recognition of dialogue, and then you have the real tone in which you would expect a service person to speak, because normal human conversations are not typically about service.
Exactly. So I think some of the research, well, the end product is probably customer facing. And in the past we've been collaborating with companies such as France Telecom, who then very kindly share their data with us, and we are able to learn from that. And now hopefully from the Alexa challenge, you know, we get a lot of data. As an academic, it's not so easy to get real customer data, as I said before. It's one of our main challenges. However, there's also the other interest is, you know, more in the lines of artificial intelligence. This is a long-standing artificial intelligence problem of, you know, trying to solve the Turing test, basically. And I think that's just a general interest of whether we can, you know, get an AI system which has these capabilities to converse. And then there's also this sort of gray area of social robotics, which on the one hand, you know, is there to support or solve a concrete task, but we also want a robot which is social and, you know, interacts with the user, and it's not purely about, you know, solving a task, but also we might want to start having a friendly relationship with your in-home robot. You know, you never know what's going to happen. Some of the current movies suggest, you know, like if some of you might see the movie Her, 2014, I think, that came out, where quite a lonely guy falls in love with its operating system, which is basically a very smart and funny version of Siri or Amazon Echo or whatever. So those are all future scenarios where, you know, seems to suggest that, you know, social interaction is part of what we're trying to achieve.
Just another question. You are speaking about very general things like social interaction and chatbots and stuff like that. What about domain-specific solutions or domain-specific interaction or analysis? Can you say something in this direction from your point of view or your work?
So do you mean by domain-specific, are they different from task-based systems?
Yes, more or less no, but the task, when you're speaking about tasks, so a task could be just to find out one apple or 3 apples. I mean, it's not really, so it's kind of a domain, but we are just, for example, speaking of medical text, or let's be technical text, so where it's more defined, where you have more or less more semantics, and where you have other disambiguation problems, I think.
Okay, so so these type of methods I've introduced earlier, reinforcement learning and dialogue state tracking, they are so far very much applied to, I'd say, toy domains, right? So one very common domain is restaurant search, because we've got some data in restaurant search, and the scientific community all trains on this data and compares, you know, their systems based on this data, which is good for, you know, figuring out whether your algorithm is better than someone else's algorithm. But if you're looking into, you know, more complicated domains, such as the medical domain, where you might also have multimodal interaction of someone pointing to the elbow and saying, it hurts here, that's something we, it's an open question whether we can actually address more complicated domains with these methods. And one crucial point, as already mentioned, is that we currently don't have large enough data sets to really find out whether it's possible or not.
I think we can have one more question.
Yeah, one question which might not be very easy to answer. I don't have a clear view on that, but you mentioned this movie where someone falls in love with an artificial being, in a way. And that made me wonder, do we actually want to have something like that?
Yeah, so the ethics of all of that is questionable. In this particular movie, there was also another movie to counteract my movie examples. There was a movie about a robot living with an elderly man, and this elderly man wasn't living a very healthy life. And the whole idea was that this robot then helped this elderly man to actually lead a more active life, and, you know, get him out and make friends and fall in love again and all of that. So the idea is that these social robots, you know, might live in your home, take care of you when you're old again. Do we want this? Maybe we'll need this at some point. I personally, to be quite honest, at the moment, I don't enjoy when I call up a call center and get one of these automated robots. I think, oh my God, not this. Where's the right button to get to a human? And that's partly what we address, right? No one likes to sit in a call center. It would be good if you had systems which actually could work properly and replace these repetitive tasks. And then, of course, there's also more of the theoretic interest of, can we solve this really hard problem of artificial intelligence, which is maybe less looking at the ethical implications of all of this. But there's certainly a strong interest in the area of robotics, for example, to get more human-like language behavior into their system and make them more friendly and more engaging to interact with.
I think this was a great question to take into the break. Before, I would like to thank you, Verena, once again. We have this self-made wine.
Oh, wow.
We have the winery in Wellsville. So
thank you very much.
And then bring it home, I hope.
Security, maybe I have to drink it first. first.
Thanks again.
Thank you very much.
We will now have a break, and since we are a little bit late, we start 10 minutes later, so that would be 10 to 11, if I'm right. And can I ask the session chairs for the next track, or for all tracks, to just come to me, and we discuss how to organize it. Okay? So 10 to 11.